SwayamPrabha. Digital India. Educated India.
Good afternoon, everybody. Today we will start a new topic on finite volume method. As we did in our earlier topic, we studied certain important aspects of finite difference methods. In this topic, we will learn the basic rules and ideas and mathematical background related to finite volume method. Next, we will do it for finite element method, and then we'll apply these methods to solve fluid flow and heat transfer problems. So let us see what we aim at learning in this topic. Finite volume method is a subdomain method with piecewise definition of the field variable in the neighborhood of chosen control volumes. The total solution domain is divided into small control volumes, which are usually rectangular in shape. This may not be exactly rectangular. We'll see later. It can have variation in shape. Nodal points are used within this control volume. That means this piecewise small control volumes. You can call it cells for interpolating the field variables, and usually a single node at the center of the control volume, the center of this cell, so to say, is used for each control volume. An excellent description of the method is available in the book of Fletcher. Also, a variant of this method was developed by Professor Patankar and Professor Spalding, and they proposed some physical ideas for the formulation of the problem and nodal equations. Incidentally, the subdomain approach based on weighted residual method and this physical approach by Professor Patankar and Spalding, you will see that they are same. Now consider a two-dimensional steady-state heat conduction in rectangular geometry, like we have given in the figure here. A 2D heat conduction equation, as you know, K del square T plus Q equal to 0, where T is the temperature field, K is the thermal conductivity, and Q is the heat generation per unit volume. So this is the overall domain, and you can see the domain has been split into small control volumes, and these control volumes are basically arranged in such a way that will be able to use their additive properties, and each control volume is identified by a node at the center of the control volume. Now, two alternative ways of setting up nodal equations, as we mentioned earlier, we will start now. The first one is weighted residual based approach. We can apply to any subdomain method. So weighted residual approach for 2D heat conduction equation, we multiply the equation with a weight function, you can see, and integrate in the domain. So this way this can be integrated in all small control volumes, and while integrating Wi equal to 1 within the ith control volume, whereas Wi equal to 0 outside the ith control volume when we are focusing at I. Thus we get for each node I equal to 1 to n the equations, and then we use the additive property to assemble these equations. Now we can write basically the volume integral here, although it is 2D equation. In a sense, third dimension is having unit dimension, third direction, and we can use this volume integral, which is equation 3. And this equation can be integrated using equation by parts, and then integration by parts, and then we can write this equation, this term, integral within the domain omega I is basically the line integral k del t dl and del t del n dl plus again the integral over omega I q dx dy. Q is the basically the heat generation rate. So where you can just refer to it, the definition of the problem, then we have reached after applying this weighted residual method technique, the last line, and then we can say how did we reach here, because here we can see basically divergence of k delta t plus q, and we can apply Gauss divergence here theorem, and then we can write convert it into basically volume integral into surface integral, but here it was surface per unit depth, so volume per unit depth. So this by applying Gauss divergence we get basically line integral k del t del n dl, and this other side is q dx dy over the domain integrated over the domain omega I. The meaning of equation 4, that means the previous equation, is that net heat generation rate, which is integral over q dx dy in the control volume, is equal to the net sum of rate of heat energy going out of the control volume. So, and this is, you can see that integral k del t del n into dl, where Ci is the boundary of the control volume. Now this can be translated in a physical sense by taking a single control volume where its center is defined at P. It has a eastern neighbor, similar control volume, that has a center at E. It has a western neighbor, a similar control volume at the western side of it, and it has a center at W, and a northern control volume which has a center at N, southern control volume which has a center at S. So considering balance of heat flux and at the interface, that means interface with the eastern cell and the cell of interest, that means at the boundary, if we consider heat flux is QE, then similarly at the western side heat flux is QW, the northern side heat flux is QN, and southern side heat flux is QS. And we can use the nomenclature. If QE is positive, for the control volume, is away from the confining surface, and it is coming to the confining surface QW, so it will be the opposite sign. So that way, QE into delta Y into 1 is the depth, minus QW into delta Y into 1. So basically delta Y is the dimension in Y direction into 1, that is the area through which QE is going out, and QW again delta Y into 1 through which QW is coming in. Similarly, QN is going out through the northern face, through here QN is going out, and QN is coming through the QS is coming through the southern face. So we have written that, and then Q, the heat generation rate per unit volume, into the total volume, that means 1 into delta X into delta Y. The net rate of energy diffusing out of the control volume through boundary. So this mode of energy transfer, we can call it diffusion, because there is no convection involved in it, no radiation involved in it. This is energy that is being conducted or diffused. So out of control volume through the boundary equal to rate of generation within the control volume at steady state. So we can summarize this as Q dot ds vector equal to Q delta X delta Y. Q dot ds is summation on all confining surfaces. So thus, assuming temperature to have linear variation between point E and P, that means again we go back to this figure, the whatever is the temperature at E and temperature at P, difference between these two temperatures will define the heat flux at QE. Similarly, difference between temperature and P and W will define the heat flux at the western surface. So we are exactly doing that. QE equal to minus K del T del X at the small e point, which is minus K TE, that temperature at the eastern point, minus TP, temperature at the center, divided by delta X. While deriving equation 6, it has been assumed that the cell size is constant in X direction. Similarly, QW is given by QW equal to minus K del T del X. So this will be minus K TP minus TW into divided by delta X, equation 7. So this way the QE, QW, small lowercase q, lowercase QE, QW, QN, QS, if we write them just what we wrote in equation 5, so we are evaluating left hand side. That left hand side, now we can write K delta T by delta X, T minus T plus TP, K delta Y by delta X. Just we are substituting the heat flux quantity multiplied by the area through which it is going out and coming in. We will get equation 8. Now if we simply substitute delta X by delta Y equal to beta, just the ratio aspect, the aspect ratio of the grid, so we will get equation 9, TP 2 plus 2 beta square minus T minus TW minus beta square Tn minus beta square Ts Q delta X square K. Now just for the aspect ratio 1 grid where delta x and delta y are same, we can very easily see this equation will be 2 plus 2, that means 4. This will be minus t plus tw, this will be again minus tn plus ts. So these are Tp means Tij, Te means Ti plus 1j, Tw is Ti minus 1j, Tn is Tij plus 1, and Ts is Tij minus 1. So this will get an algebraic equation, exactly what we got following finite difference method, if you recall. And from there, either explicitly we find out what should be Tp, and then we iterate it over every Tp, that means over every Ij, or we do the implicit formulation. We express Tij as unknown in terms of all his unknown neighbors, and we run from cell 1 to the last cell, and Ij varies, we get the system of algebraic equations. So during the numerical implementation, we have written the subscripts E, W, etc. will be changed to numerical indices of Ij and solved the same way as we discussed earlier. Now we will discuss two special situations. That means formulation part we have discussed. We have to discuss boundary conditions. Now see here we have discussed about Neumann boundary. That means, see, if on one phase, if heat flux at x equal to 0, for example, if heat flux is defined, that will be equivalent to Neumann boundary condition. So the control volumes adjacent to x equal to 0, all these control volumes adjacent to x equal to 0 boundary, as shown in figure 3, the term QW will be substituted by Q naught, because Q naught is specified. Q naught is basically thermal conductivity into the thermal gradient on this phase, which is del K del X. If that is defined, then that means Q0 is defined. So then equation 5 means our earlier this equation. Here we will just while evaluating, we'll write QE into delta Y, eastern phase, it is going out. Any cell we take through eastern phase, QE into delta Y. Through western phase, we can write Q0 into delta Y, which is coming in, and then Qn into delta X to northern phase minus Qs into delta X to the southern phase, and then QE we explicitly write T minus Tp by delta X into thermal conductivity K with a negative sign. Qn also we write its expression, Qs we write its expression, and basically Q naught into delta Y, leave it like that because Q naught is now specified, equal to uppercase Q, heat generation rate, into delta X delta Y. Equation 10, this will be the governing equation for all the cells that are having from western side defined heat flux. So in this symbolic equation, if we can substitute the P as ij, and eastern neighbor, western neighbor as I plus 1j, I minus 1j, etc. We'll be able to set up again nodal equation on the nodes where the boundary condition is known. Now boundary condition is known but Norman boundary. Now we will go for the Dirichlet boundary condition. And we have given a typical grid distribution. Here you can see P is the point of interest, W is the western neighbor, S is the southern neighbor, N is the northern neighbor, and the boundary condition at x equal to L is known. Now x equal to L, ideally this point is the eastern neighbor. The cell also eastern neighbor cell, but this point is falling at the edge or at the end of the boundary, and we know the temperature here TL, since it is Dirichlet condition. So our formulation will be slightly more involved. So TL has to be substituted instead of T in the nodal equation, and so that the boundary condition can be directly applied. So if we write that for eastern neighbor there is no problem, western neighbor no problem, northern neighbor no problem, southern neighbor no problem in writing this. But when we specifically substitute their value, you can see we have written minus k TL minus TP. So this is now L. So eastern point, it is TL minus TP, and the grid size is also changed, divided by x by 2 into delta y. Then western neighbor remains similar expression, TP minus TW by delta x into k. So into delta y. Northern neighbor remains same, southern neighbor expression we have whatever we have done earlier, and Q into, but here this for heat generation the volume is not delta x into delta y, but this is basically you can see we have written delta x1 is 3/4 delta x. So heat generation rate is delta x1 into y, not delta x into y. Delta x1 means basically 3/4 delta x. So let us explain this. Now when the boundary is specified, that means the eastern node, all eastern nodes are now basically temperatures will be TL. When the boundary is specified, the control volume shapes near the boundary can be changed to facilitate the implementation of the boundary conditions. For instance, consider the condition T equal to TL on the x equal to L. Say the domain starts somewhere at x equal to 0. At x equal to L, all TLs are known. For the nodes on the boundary, an imaginary extension of the control volume outside the actual domain can be considered in line with the finite difference methodology described earlier. So we are thinking as if this node is surrounded by a cell, and this is the cell, although this one part of the cell is falling outside the boundary, and this is not really truly physical. So that's what we have done. The physical boundary taken to be the center of the boundary cell with delta by 2. So this is the physical boundary of the neighboring cell, and this is the basically this delta by 4, delta by 4, we have done these extensions, and the physical boundary is taken to be center of the boundary cell of width delta x by 2, while the width of the adjacent cell are reduced to 3 delta x by 4. So this cell width is not now full delta x, because 1/4 has been taken away while defining this cell, which is not pseudo cell, real cell, but this real cell is having a dimension delta x by 4 in either side. So basically the boundary cells will need no nodal equation, as the condition T equal to TL will be applied. The nodal equation for the adjacent cell P will be written considering then shorted control value. So again, let us go for what we wrote earlier, Q E into delta y minus QW into delta y plus Qn into, here it will be delta x1, right, and Qs into delta x1. So this dimension is change dimension, and we are calling it delta x1, delta x1. So basically minus k TL minus TP divided by delta x by 2. So now this distance is delta x by 2 into delta y. K TP minus TW, this distance remained as delta x, minus k Tn minus Tp by delta y, Tn minus Tp by delta y, this delta y remains same, but this will be multiplied by delta x1. Similarly, k Tp minus Ts, this will also be multiplied by delta x1, where delta x1 is basically 3/4 delta x, and heat generation rate is also Q delta x1 into delta y. So basically you can see that these nodes we are directly writing TL, we are not generating any equation for them, but the equation for P with respect to all neighbors, when we are expressing that, we write here the flux TE minus TP or TL minus TP by delta x by 2. Here we write TP minus TW by delta x. Here Tn minus TP by delta y, and here TP minus Ts by delta y. And when we multiply the area here through which flux is coming, here it is delta y into 1, here it is delta y into 1, but here it is 3/4, here it is 3/4 3/4 delta x, here it is 3/4 delta x into 1, here it is 3/4 delta x into 1. So that is the difference, and this way now we can set the equations. So rethink about it, how the boundary condition, when it is Dirichlet, how boundary condition is defined, and since it is directly on the node, no nodal equation is generated for these points, but the inner points, for example, when this is P, what should be the equation, we have come to know. So philosophy is same, heat flux in this direction. Only thing, while deciding heat flux, it will be decided K into TE minus TP divided by delta x by 2. And here it will remain same, K into TP minus TW divided by delta x. Here it will be Tn minus Tp by delta y. Here it will be Tp minus Ts by delta y. And K is obviously there with all the heat fluxes. And as I said, area of concern, here it is delta when it is heat flux between E and or L, TL and TP, then area through which it is crossing is basically delta y into 1. Between P and W, again delta y into 1. But when northern node and P node are involved, this heat flux, that means Qn, here the area, multiplying area will be 3/4 delta x into 1. And similarly between the southern node and the node P, the heat flux will be multiplied by 3/4 or delta x, 3/4 delta x into 1. And energy generation rate also will be considered within this control volume. And we don't, this dotted control volume, we don't write any equation. This is represented by a point where temperature value is directly known, or the value of the dependent variable is directly known. So today's first lecture on control volume, we can say that what we have studied is the following, that by adjusting the control volume spacing and the placement of nodes, nodal equations can be obtained at all nodes, and these can be solved simultaneously by the matrix inversion technique. So we are talking about implicit formulation. That means, basically node of interest P will express in terms of neighbors, and while expressing, if neighbors are represented they are by their node number, then they will come straight away. If the neighbors are represented by boundary condition, then we'll adopt the boundary condition. That means all this while formulating the problem, neighboring nodes to the boundary, those are to be paid special interest, special attention, and then we'll be able to get the algebraic equations. If we run I to 1 from 1 to I max, and j is a node number from 1 to j max, j maximum. So this can be solved simultaneously by matrix inversion technique, or line by line technique, or point by point technique. As discussed earlier, the point Tp will be substituted by Tij, Te will be substituted by Ti plus 1j, Tw will be substituted by Ti minus 1j. Similarly, Tn will be substituted by Tij plus 1. Ts will be substituted by Tij minus 1, and so forth. Having done the above exercise, we may like to look at a more generalized. So this is, basically a Cartesian coordinate we have used here. So grids are straightforward. What we try to focus at, the formulation is based on integral technique. Everywhere we are integrating and finding out the nodal equation, and this is different from the finite difference method. We are not like finite difference method. We are not following or forming the different quotients and substituting different quotients in the differential equation. Rather, we are, unlike that, we are integrating it over the control volume, like as I said, that equation 11 or equation any equation you take, or equation 9, these, although since the geometry is simpler, it is in Cartesian coordinate, and in delta x, delta y, the grid spacing is also regular. So we'll get exactly, if we express Tp, T, Tw, T and Ts by Tij minus 1, Tij plus 1 for northern node, and Ti plus 1j for eastern node, and for Ti minus 1j for Tw, then we'll get an equation which we also get in finite difference method. But here the methodology we followed is different. We integrated the fluxes on the faces, through which fluxes are passing through, or going from one cell to another cell, or going out of the domain as the boundary and boundary condition is being defined. So this is the difference. But even then, expression what we got, expression is the same if we take Cartesian coordinate and we integrate it on the Cartesian control volumes, smaller control volumes. But as I have mentioned here, the last line, that in complex geometry, grids will be curvilinear grids, and grid mesh will be complex, and there then the same integration technique, but we have to improvise. We have to see how to improve this integration technique so that the integration can be done on the curved surfaces in order to balance the fluxes. So we will stop here today. We will take up these aspects in the subsequent classes. Thank you very much.